Chapter 2, Picturing Variation with Graphs. This is Math 114, test number 1 packet, and it's part 2. And a reminder down at the bottom, the textbook Essential Statistics, Exploring the World Through Data is the textbook that's referenced throughout this packet. Okay, this video starts with Chapter 2.1, Visualizing Variation in Numerical Data. All right, number 1, let's start by taking a look at a data set from the roller coaster database. The following data contains information about the maximum speed in miles per hour of the roller coaster for the wooden roller coasters. So we can see that there are 46 roller coasters in this data set. Type is listed as wooden for each one, and then the speed is also given for each of these roller coasters. So taking a closer look at this table of data, I want to see what it reveals about the maximum speeds of the roller coasters. And so what does this table of data reveal about the maximum speeds of the roller coasters? And what do you think is a typical speed for these roller coasters? So first glance, it's kind of hard to tell, hard to answer this. It's somewhat subjective. If you're thinking about typical speed, that's to be something in the middle. So some of you may answer that it's somewhere around 50. And so if you look through the table of data, you see a lot of 40s, 50s, and 60s. Looks like the speeds go anywhere from, I think I saw a minimum here of 25. And if we look for a faster speed, looks like some of the faster ones up in the 60s. I do see one here that's at 78. So again, typical is hard to tell, but for most of us, that's something in the center. So for now, I'm going to say that's somewhere around 50 miles per hour. Okay, number 3, it's usually difficult to detect any patterns or key features of a data set when it's presented as a list of values. One important tool for investigating the variation in a set of data is the distribution of the data. If this data comes from a sample, then this distribution is referred to as a sample distribution. We can also say distribution of the sample. Your book uses both terms. Okay, so sample distribution can also be referred to as distribution of the sample. A sample distribution organizes data by recording all of the values observed in the sample, as well as how many times each value was observed. These sample distributions can appear in table form or in graph form. Okay, so number 4, the frequency table below contains the sample distribution for the roller coaster data set. Notice that this table lists the maximum speeds and also the frequencies, which is how many coasters reach that maximum speed. So for instance, up in the top row, we can see that the speed of 25 miles per hour only occurred once. If you go somewhere in the middle, here's another example. 55 miles per hour had appeared 6 times in your data set. 6 coasters had a speed of 55 miles per hour. So notice that this frequency table gives us more information about the data than the list of values did. We can also say that it's more convenient or easier to read. Speeds are listed from least to greatest, so it's also organized in a better way. And the frequencies are tabulated. And so we can right off the bat see the minimum and the maximum speeds, and see the frequencies, and now it may make it easier to see what we think is a typical speed. So again, typical, if we think of something in the middle, we might pick a speed somewhere in here. But that again is somewhat subjective right now, so you may have a different answer than somebody else. Number 5, a picture or graph can make it even easier for us to see patterns and is often our first step in analyzing the following key features of a data set. So when we look at a distribution of data, we're often interested in what is its shape, where is its center. This is another way of asking what's a typical outcome. And the third thing is variability, which is also referred to as spread. We're going to take a closer look at these in section 2.2. There are 3 graphs we're going to be using for numerical data. First one is a dot plot. We're also going to look at a histogram and a stem plot. And so as an example, in number 6, we've got a dot plot. A dot plot is a graphical summary that shows a picture of the distribution of a numerical variable and can allow us to detect patterns in the variation of a sample of data. So here, distribution, keep in mind that this shows the values in your data set. and also shows the frequencies. So very similar to the table above, and shows the values and the frequencies of these values. So if we take a look at our dot plot, we can also see very clearly where does it start, what's its minimum value, what's its largest value. We do have to do a little bit more work in terms of how it compares to the table because this doesn't have a number below it. So we have to figure out a scale. So if we look more closely, there's 1, 2, 3, 4, 5 spaces between 20 and 30. So we know that this goes 22, 24, 26, 28. So we can confirm this first dot is at 25 miles per hour. And this last dot, we've got 72, 74, 76. This last one is at 78 miles per hour. We can also see here that 50 is a speed that occurs more often than any others. In fact, that there, if we count the dots, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 coasters with a speed or a maximum speed of 50 miles per hour. Okay, there's some key features of a dot plot. I'm going to flip back and look at the dot plot from the previous page while we go through these. All right, so first thing, the variable name is given on the horizontal axes. So you always want to make sure you include this. Here's our variable name in this case. Second thing, there's no vertical axes. So if you look over here, although there's a line there, there's no scale on it. So no vertical axes or no vertical scale is given. And the reason for that is that the height of these piles tells us what the frequency is. So the number of dots above a specified speed tells us how many roller coasters have that maximum speed. So again, here's our example. We got 9 coasters with a max speed of 50 miles per hour, and the number of dots in that pile tells us that. Next thing on the list, the axes uses a consistent scale. We saw that here. This is a consistent scale, meaning each space, equal size spaces, have the same amount of numbers between them. So as in another example, let me see if I can get some more space on here. Doesn't look like it. So we would not want to use something that goes 5, 10, 100, say 1,000. This would be an example that's not consistent. So I'm going to put a big X to this. Don't want to do something like that. And then the last thing under key features of a dot plot, each observational unit is represented by a dot. So the number of dots is equal to the number of observational units in your data set. So if we wanted to figure out how many coasters were in this data set, we could count the number of dots. Okay, number 7, dot plots are fairly easy to make if the data set is relatively small. If the data set is too large to produce a dot plot by hand, then either technology can be used or a different type of graph can be produced. Number 8, one of the earliest statistical graphs dates back to 1786. A Scottish engineer named William Playfair produced a graph to examine whether there was a relationship between the price of wheat and wages. And if you would like a better picture of this graph, it might be easier to read. You can find one on page 37 of your text. And it's just interesting to note that this graph became the prototype of 2 of the most commonly used graphs, the bar chart and the histogram. Okay, so let's take a look at a histogram. So number 9, another type of graph for numerical variables is a histogram. Histograms are more useful and easier to create for larger data sets. Histograms group together observations into intervals or bins, and they can also be called classes. So if you take a closer look at this histogram, notice that the frequency is now on the vertical axes. The variable name is still on the horizontal axes. And again, frequency on the vertical axis, we need a scale here. And notice it's a consistent scale, just like on the horizontal axes. And that's because we don't have piles of dots anymore. So it's the height of the bar that's going to give us the information. All right, so this histogram again contains the maximum speeds for those wooden roller coasters we were looking at in the dot plot before. Right. So a few questions about this histogram. So number 10, use this histogram to answer the following questions. First one is, what are the endpoints of the first bin or interval? So if we look, here's our first bin right there. We want to figure out, where does it start and stop? What are its left endpoint and its right-hand side endpoint? So knowing that there's a consistent scale, if 40 is here and 60 is here, then halfway between them must be 50. And if we look halfway between 40 and 50, this must be 45. So 45, 40, if I count backwards, I get 35, 30, and 25. So the endpoints of the first bin or interval are 25 and 35. B, what is the height of the first bin? And that's where that vertical axis, or the scale in the vertical axis, comes in handy. The height of this bin looks like it's at 1. So that tells us there's one roller coaster, oops, in the first bin. Make that a little bit more legible. Part C, how many roller coasters had a maximum speed of 65 miles per hour or greater? We come up here, our first step is we've got to find where 65 is on our graph. Here's 65 miles per hour. So 65 miles per hour or greater, we're going in that direction. We want the height of this bar and the height of that bar together. So this first bar appears to have a height of 6, and this bar has a height of 1. So we've got 6 plus 1 gives us 7 coasters that had a speed of 65 miles per hour or greater. And then the last question here, D, how many roller coasters had a maximum speed of 70 miles per hour or greater? This one's a little bit different. Notice that 70 is the midpoint of that interval, which means inside that bin, we don't know how many coasters had a speed of 70, how many had a speed of 69 or 71, or any of the speeds in that bin. So we can't actually answer this one. And that's one of the drawbacks of a histogram. We go back to the table of data, we could answer it. But with a histogram, we can't do that. Okay, one other note on this before we continue on. Typically, and this is a convention, so typically means it might not always be the case, but typically the left-hand side endpoint, or the left endpoint, is included in a bin. Okay, so if we look at this last bin, let's say right here, that goes from 75 up to 80. That means it includes the speed 75, 76, 77, 78, and 79. 80, if there was a speed of 80, would be included in the bin to the right. So again, typically the left endpoint is included in a bin, but the right-hand endpoint goes with the next one. Okay, some key features of a histogram. The variable name is given on the horizontal axis. Frequencies or relative frequencies are given on the vertical axes. And we'll take a look at relative frequencies in the next activity. The heights of the bins tell us how many or what proportion of the roller coasters fall within an interval or of maximum speeds. Axes use a continuous and consistent scale. Individual values are no longer visible to us, so we lose a little bit of detail. And they're useful when the data set is too large to create a dot plot without technology. Okay, number 11, let's create a second histogram for this data set that has a greater number of intervals. Use the following steps and axes given below. All right, so first step, identify the minimum and maximum speeds in this data set. So our minimum is 25, our maximum is 78. Next step, we're going to subtract these values. So note the difference between the maximum and the minimum values called the range. So 78 minus 25 gives us a difference of 53. In C, since we're going to create a histogram with a greater number of intervals, we need a smaller bin width. Let's consider a width of 5. So we're going to divide this range by 5, and this is going to give us roughly the number of bins in our histogram. So if we take 53 and divide it by 5, we get 10.6. So we might use a bin, or we might have 10, or we might have 11 as our bin width. Oh, sorry, excuse me, as the number of bins. So the other note here is dividing the range by the desired number of bins can give you the rough width of the bins. All right, so in part D, our first interval is going to start at our minimum value, or value pretty close to that. Let's use 25 miles per hour. So we're going to mark this value on our horizontal axes. And since the width of our intervals is 5, we're going to continue to mark the values on the horizontal axes that are 5 apart. These values are going to become the endpoints of our intervals. So here's 25. I'm going to make a mark at 30, 35, 40. Keep going, they're all 5 apart. Fortunately, our axes has these marked for us already. And then we're going to count the number of observations that fall within each interval and draw a bin for each interval with the appropriate height. So we need to look at our first interval from 25 to 30. It's just going to have 1 coaster in it. Let's come back down. We'll put a height of 1 for that first bar. Then I'm going to go back up. We've got 30 to 35, 35 to 40, and 40 wouldn't be included because it's the right-hand side. But then 40 to 45, we're going to have 2 coasters. And I'm going to keep marking these while we're here at the table. Our next bin width is going to go 45 up to 50. So we're going to have a total of 6 coasters in that bin. And then 50 to 55, got a total of 14 coasters there. 55 up to 60, got a total of 10 coasters in here. And then 60 to 65, got 6. 65 to 70, we've got another 6. And this last one is going to have 1 coaster in it. So we got to come down and use those numbers for our heights. We're going to see that our next bar from 40 to 45 has a height of 2. Okay, and then from 50 to 55, but I skipped 1, 45 to 50, we're going to have a height of 6. Okay. And then we need a height of 14 for our next bin. That's roughly here. And then we need a height of 10 for the next one, about here. And then heights of 6 for the next 2 bins. Okay, and then a height of 1 between 75 and 80. And once I'm done, I'm going to erase these dashed lines that help me with the heights. And there's our histogram. Okay, so which histogram do you think is better and why? That's somewhat subjective as well. So notice that this histogram has a few more bins than the other one, so it's giving us a little bit more detail. Right, and we'll explore this question a little bit more detail as well in your activities today. Okay, so number 13, how many bins are best for a given histogram? Again, we'll take a look at that question in the group activity at the end of class. Keep in mind the histograms are meant to provide insight, not answers. If the distribution looks multimodal, which means it's got a lot of groups or clusters to it, we should ask ourselves why this might be. Choosing wide bins may hide the important details such as shape. Choosing 2 small bins might make every distribution look like it's got a lot of different clusters, a lot of different groups. So you have to be careful about that. Typically, we find that a good rule of thumb is between 5 and 15 bins. But every data set is different. Okay, so number 14, we're going to use the following axes to create another histogram. This time it's going to be a relative frequency histogram. Relative frequency histogram displays the relative frequencies on the vertical axes. Reminder, relative frequency gives the proportion of the 46 roller coasters that fall within each interval. So be sure to label the vertical axes. So our first step is to calculate the relative frequencies. So remember that there were 46 coasters. So n equal to 46 coasters. N is just the symbol we typically use for a count or a sample size. So for instance, in this first one, there was 1 coaster. So we found 1 out of 46 was 0.022 or 2.2% if you're more comfortable with percentages. The next one would be 0 out of 46 or 0. And I'm going to press pause and fill these numbers in. I suggest that you do the same. Okay, so I have those relative frequencies filled in now. And we're going to include those in our relative frequency histogram down here. So note that the vertical axis is now going to be referred to or labeled as a relative frequency. You could also put proportion or percent. Okay. All right, our horizontal axis still has the speed. We want to label these. So we need to go roughly up to, I think 30% was our largest one. Let's say this is 10%, 20%, 30%, 40%. Okay. So our first bar starts at 25 and has a height of about 2%. So we have a fairly short bar here. And then between 40 and 45, we've got a height of about about 4%. Oops. Right about there. It's probably a little too tall. And then 45 to 49, we've got about 13%. Right about there. And 30% roughly for the next bar. So here. And then we've got 21% for the next bar. There. And about 6% for the next two. And then one tiny bar over here at about 2%. So notice this doesn't give us anything really different from the previous histogram. It's just that the vertical axis has been rescaled. Okay, number 15, another type of graph for numerical variables is a stem plot, or it can also be called a stem and leaf plot. These graphs are also useful when the data set is small and you don't have access to technology. So number 16, let's create a stem plot for the roller coaster data by following the steps below. First step, we're going to divide each value into a stem and also into a leaf. So leaf is typically the last digit of the value, and the stem is typically the digits that precede the leaf. We're going to use the last digit, which is the ones digit, and each value is our leaf, and the first digit, the tens digit, in each value is our stem. So for example, a speed of 65 miles per hour, this would be our leaf, that's our ones digit, and this is going to be our stem. This is our tens digit. Okay. In part B, the stem is filled in for us in the graph below. The leaves for each speed less than or equal to 60 miles per hour are also filled in for us. We're going to write in a leaf for each observation that has a speed greater than 60 miles per hour. So greater than 60, we've got to look at these roller coasters down here. So note, there are 4 speeds of 60. Here are the 4 speeds representing those 4 coasters. So if I continue on, I want to use the stem that's labeled with a 6. Right, for 62. So I'm going to add a leaf at 62, and I need to do that twice because there are 2 coasters with that speed. There are 4 coasters with a speed of 65. So I need 4 leaves to represent those 4 coasters. And there are 2 coasters with speeds of 66. So I need 2 more leaves in that row. And then our last coaster has a speed of 78. So we're going to put a leaf down on that portion of the stem. And with all of these, we want to make sure we include a legend or key at the bottom, giving somebody the ability to interpret this. So we might say, for instance, 2, and then we use that vertical line to indicate what separates the stem from the leaves. 5 is 25 miles per hour. Okay. So note the stem plot is referred to as an ordered stem plot since the leaves are arranged in order from smallest to largest. If you're doing this by hand, you might start with an unordered stem plot, kind of your rough draft, and then order it as your second step. And last thing we want to make sure we do is put a title on here. So up here, we might want to say that these are wooden roller coaster speeds, or wooden roller coaster maximum speeds. Okay. All right, while you have that in front of you, take your paper if you have it printed out and try rotating your stem plot 90 degrees. Notice that it now resembles both the dot plot and the histogram, but has the added benefit of displaying all of the actual values in the data. So if I try and rotate this, I'm probably going to lose most of the leaves I just put in. Oh, actually, I can't do that. Forgot pictures can't be edited in here. All right, so I'll leave it up to you to take your paper and turn it. Right. Next thing, key features of a stem plot. Keep in mind that numbers are divided into leaves and stems. Leaves are typically only 1 digit in length, although you will on occasion see leaves that are 2 digits in length. Stems are written in a vertical column, and the associated leaves are written to the right of the stem. They're useful when you don't have access to technology and you don't have a very large data set. The variable name is given in the title of the graph. A key or legend should be given to inform the reader of the graph what the size of each entry is. For example, the key above was 2, and again, that vertical line indicates what separates the stem from the leaf. 2.5 is 25 miles per hour. There's no horizontal axes. The number of leaves to the right of a specific speed tells us how many roller coasters had that maximum speed. So it's similar to a dot plot in that way. Each observational unit is represented by a leaf. The number of leaves is equal to the number of observational units in the data set. And stems are not omitted when they don't have leaves. The stem should be continuous. So I'm going to flip back just for a moment to our stem plot. Good example of that is right here at 3. Even though there were no speeds between 30 and 40 miles per hour, we still include that in our stem because it needs to be continuous.